We've all heard the saying that time is fair to everyone. But what exactly is time? Some say it is a personal perception, while others consider it a physics problem. You could also say that time consists of the past, present, and future. You experience the present, slowly leave the past behind, and the future gradually approaches you. This is the linearity of time. You ate an egg this morning. You read a newspaper last week. These are experiences that cannot be repeated as time flows. However, today I want to tell you that time is not a parameter but a dimension. After understanding this, I will prove to you that the past has not disappeared due to the passage of time. It still exists in a physical sense. After watching this film, you will also understand that time is not necessarily fair to everyone. Before we discuss time, I must introduce the concept of space. Imagine a line with a bee on it. The bee can only move along this dimension throughout its life. This is its trajectory, an example of a one-dimensional creature. If a beam of light crosses its path, it can only perceive the light when it intersects the line, but it cannot see the light outside the one-dimensional space. Then one day, another line appears, perpendicular to the original one. This is the second dimension. Our bee now moves from a point to a plane and can move freely on this plane. It becomes more lively and interesting, and it can see the light passing through the entire plane. However, the two-dimensional world has no thickness. If the light changes angle, the bee will not see it outside the plane. Next, we add another line perpendicular to the previous two lines, and we enter the three-dimensional world. The bee evolves into a more interesting creature, and its world expands infinitely. It can observe light from any direction. So, how do we enter the fourth dimension? Those familiar with Einstein's theory of relativity know that the next dimension after three-dimensional space is time. However, no one has seen what the fourth dimension looks like. This is because, to enter the fourth dimension, we must draw a fourth line perpendicular to the previous three lines, which is impossible, right? Yes. It is impossible in three-dimensional space, just as the bee in one-dimensional space cannot see the light in two-dimensional space. However, this does not prevent us from imagining the fourth dimension within the known space, much like this three-dimensional drawing existing in two-dimensional space. We just need to train our brains, and we will soon understand. Let's understand this from the simpler two-dimensional space. Look at this chart. The vertical axis represents time, and the horizontal axis represents three-dimensional space. Their coexistence is space-time. Here is our little bee. If it remains still, its trajectory over time looks like this. However, if it buzzes away joyfully, its trajectory will look like this. As the bee's flying speed increases, we observe that its trajectory gets closer to the horizontal axis. This explains why time slows down as speed increases. When the bee's speed reaches the speed of light, we can say that time completely stops. How should we understand the theory of relativity of time? Let's make the picture more interesting by glimpsing into the four-dimensional space from the three-dimensional perspective. The red plane represents three-dimensional space, and the vertical axis remains our time axis. Now, let's add a frog. This is a lazy creature, staying still in one place. Over time, it moves uniformly along the time axis. Our original bee, although not reaching the speed of light, flies at a relatively fast speed compared to the frog. Thus its posture looks like this. After some time, the bee gets tired and stops flying. At this very moment, a magical thing happens. Let's return to the two-dimensional perspective to look at this event. We find that the frog and the bee are at different points on the time axis. More precisely, the bee experiences a dilated, slower time, while the frog experiences a longer duration. For the bee and the frog, they end up standing on different points of the time axis objectively. However, nothing strange happens in their world. Therefore, theoretically speaking, it is feasible for someone to return home after high-speed interstellar travel and find themselves the same age as their sun. Einstein proposed a famous thought experiment to better help us understand the past and future within the framework of special relativity. But before that, we must agree on the premises of Einstein's special relativity, which are: the speed of light in a vacuum is finite and constant. No object can exceed the speed of light. Every observer's perspective is valid. The experiment involves two people. One person is stationary, let's call him A. The other person, B, is at the midpoint of a high-speed moving train. When the train passes by A, the signal lights at the front and rear of the train light up simultaneously. For observer A outside the train, the two signals light up at the same time because the distances from both light sources to A are equal. However, for observer B inside the train, the front signal lights up first, followed by the rear signal. This is because B is moving towards the front signal and away from the rear signal. Naturally, the light from the front signal reaches his retina first. According to special relativity, both viewpoints are valid. Next, we will delve into the main topic, where I will demonstrate why the past still exists. To define the past and the future, we also need a time coordinate, which is the present. On this basis, let's assume both A and B have a specially designed photon clock. This clock consists of two opposite mirrors with a photon bouncing back and forth between them. To better understand each person's perception of time, we tell them that the exact moment when the photon is in the middle of the mirrors is the observation point to record, which we call now. A's clock is stationary, while B's clock is moving at high speed. In this case, the photon's trajectory looks like this. It is evident that the distance traveled by B's photon is greater than that of A's. The speed versus is equal to the distance d divided by time t. We know the speed of light has a limit and remains constant, so the only explanation for this equation is that B's clock runs slower. Therefore, when A records his observation point, B's observation point has not occurred yet. Remember the premise of special relativity? Every observer's perspective is valid. Understanding this, we can say that A's and B's present moments are not in the same spacetime. In other words, A's past and B's present are on the same time axis. By the same logic, if a third person, C, moves even faster than B, then A's even earlier past would be on the same time axis as C's present. C's present is A's earlier past. If this concept is acceptable, we can confidently say that everyone's past exists in this universe, like pages stacked one on top of another. If you already find Einstein's special relativity incredible, I have an even bolder hypothesis. Let's randomly select the coordinates of two completely unrelated events in spacetime. For example, a flight from Dublin to Barcelona landed on time at 10 a.m. yesterday, and you accidentally broke a glass today. For an observer moving at the right speed and positioned equidistant between these two events, the light from both coordinates would reach them simultaneously. Therefore, for this observer, these two events occur simultaneously. By the same logic, two causally related events, such as the day you met your spouse and the day your child was born, could also appear to occur simultaneously for a particular observer. We ordinary people don't have the opportunity to travel at high speeds in spaceships, but this doesn't prevent us from becoming super observers. For instance, the starlight we can see with the naked eye comes from stars 200 to 2000 light-years away. What we see now is actually their past. On September 18, 2006, humans observed the explosion of the supernova SN 2006 GY, which is 238 million light-years away, using an astronomical telescope. This means that when we saw its explosion, it had actually died 238 million years ago. In other words, when the earliest dinosaurs were just emerging from their reptilian ancestors, this star had already reached an end stage in its life. However, it wasn't until 2006 that humans observed it. Its past is our present. However, not all events can be observed. For example, we currently cannot observe events occurring inside gravitational singularities or spacetime singularities. These points have an infinitely small volume, infinite density, infinite gravity, and infinite spacetime curvature, absorbing even light. This is another topic for another video in the future. At this point, I imagine everyone has a question. We can move freely in all directions within the three-dimensional world, but why can we only move in one direction in the fourth dimension? Returning to our initial topic, if we can observe our past, why can't we go back to it? Why can't we prevent our past mistakes and change our destiny? The second law of thermodynamics provides the answer. Time is closely tied to the behavior of entropy. Entropy measures the degree of disorder in a system. Compared to a statue, sand is more chaotic and disordered, thus having higher entropy. If we throw a statue into a river, after many years of erosion, it will turn into sand. However, no matter how many years pass, sand will never form into a statue. Therefore, the laws of the universe dictate that in an isolated system, entropy can only increase. We consider the direction in which time flows as the forward direction, which is also the direction of increasing entropy. In other words, if one day we find a naturally formed smartphone or a fully assembled electric car on the beach, it would mean that the laws of the universe have allowed time to flow backward. But until then, please like, comment, and subscribe to my channel. Your support is my greatest motivation to create videos for you. I hope you enjoyed today's video. See you next time.